going to look at molar mass and density. With our gas laws, we're able to kind of rearrange them, use some other like density equations and substitute into those gas laws and find molar mass and density of a gas. Our goal. Okay. So for, well, the number of moles, if we want to find the number of moles, it's the molar mass, right, which is the mass per mole. Or if we're going to convert that to grams, yeah. So that's where we get, that's how they get this M and M in here. They substituted that in for N, and PV equals nRT. So then they rearrange this, and big M is your molar mass. And then M is the mass of the actual mass of gas that you have. So if they say you have 32 grams of carbon dioxide gas or something, that would be 32 right there. M is the molar mass of the gas, so you'd have to calculate carbon plus 2 oxygens. And then RT, PV, those are all the same as we've used before. So that's our molar mass equation.
Wait, what is R?
R is 0.0821, that same ideal gas constant. Okay, our density equation, D equals M over V, all right, way back from chapter 1. And so if we rearrange that, we have in this equation right here, M over V, right, we have, right here we have M over V. Let's circle that. So that would equal density, right? So that's how we would have M equals dRT over P. So they rearrange for density, so D would equal PM over RT. And that's how we get that equation right there. So all they're doing is taking equations that we already know, substituting some stuff in for it, and then getting another equation from that. So that way you don't have to convert, or you won't have to find moles and then code grams and whatever, or you won't have to find molar mass and then go and do density. You don't have to do 2 equations. They've already substituted 2 equations in, and then you only have to do 1 equation. Kind of makes it a little simpler. So questions on those two? We do some problems. So first problem, at 28 degrees Celsius and 0.974 ATM, 1 liter of gas has a mass of 5.16 grams. What's the molar mass of this gas? So what's our equation? M equals
MRT over PV.
So what's the molar mass? We're looking for big M, right? What's the mass of our gas?
Wait, say 5.16.
5.16. R 0.0821. It's our temperature.
Do we need to change it to Kelvin?
Yes, we need to change it to Kelvin.
301.
301? But since we're using R, remember the units for R have Kelvin in them. So we have to use Kelvin, we have to use liters, we have to use ATM.
You can't use milliliters?
Can't use milliliters
Well,
whenever you're using R.
When you use R, we use milliliters.
We have to use liters. So our pressure is 0.974, and our volume is 1. So, what's our molar mass?
I
.2476.30.
got 130.
Yeah, I
Yeah,
got
wow.
130.9. Okay. 130.9. What would be your units? Grams per mole, because remember the units here, what do we have? We have ATM times liter over mole per Kelvin. That's our units for R. So our ATM canceled out because we're dividing by an ATM. Liters canceled out because we're dividing by liters. Then this one, we're multiplying by a Kelvin, so our Kelvins canceled out, but we didn't ever multiply by moles, so that's got left. And then the units for 5.6 were grams, so we're left with grams per mole as our units.
So the mass of the gas always has to be in grams then too.
Right.
Okay.
If they give you moles, you can use PV equals nRT, or you can convert that
Oh.
into, I guess convert that into grams then, and then use this equation,
Okay.
depending on what you need.
Yeah.
Okay, next one. What's the molar mass of a gas if 0.47427 grams of the gas occupies a volume of 125 milliliters at 20 degrees Celsius and 0.98 ATM?
You need to change the 125 milliliters to liters, which would be 0.0125 liters.
Just 0.125. And that would be on the bottom, right? Because we're dividing by PV. Pressure is 0.98. And little m, mass of gas.
0.427 grams.
R is 0.0821. Temperature would be 293, right? So, big M equal 0.427 times 0.0821. That's 293 divided by 0.98 divided by 0.1.
83.8.
What was that?
83.8.
83?
Yeah.
And again, we're in grams per mole, right? You agree with that?
I'm not having fun right now.
Now, if you're gonna put 0.98 times 0.125, make sure you put parentheses in your calculator around the 0.98 times 0.125. Otherwise, it'll divide by 0.98 and then take that total and multiply it by 0.125. Or you can just push divide by 0.98 and divide by 0.125. Okay, the next one has to do with densities. We're using that other equation, which was what? D equals,
PM over RT.
Wait, what was that last answer?
83.8.
I got 84.0.
One of your decimal, or one of your numbers must be wrong.
I'm not at 7 things.
Check your numbers at 800, remember that, right? Okay, what's the density of a sample of ammonia gas, so NH3, at the pressure of 0.980 ATM and the temperature is 63 degrees Celsius?
So do we have to find big M first?
What would be big M? How would you find that?
Um,
Big M is what?
Molar mass.
Molar mass. So we 17 plus 3 hydrogens, so that would be 17. So our pressure is 0.98 times 17 divided by R is always 0.0821. Temperature, we have to be in which units?
Kelvin.
Kelvin. So what is it?
336.
336? So our density of the gas is
Where did you get the 336?
that is the temperature, but we gotta change this to Kelvin. So you add 270.
0.6.
0.6?
Yeah.
Okay, so where'd you get the 17?
Yeah.
17 molar mass of NH3,
7.
right? Nitrogen is 14 plus 3 hydrogens gives you 17. Right?
Nitrogen is 14.
Nitrogen is 14.
Oh, okay, I see.
And what's gonna be our units? Let's check this out. So remember R has, what do we have, ATM over, or times liters over mole Kelvin, right? So this is an ATM, our pressure is an ATM, so this cancels out right here. This here is Kelvin, so that cancels this out. And then our units here are grams per mole. So the units here cancel out, so we're left with
Liters and grams?
liters and grams, but grams is on top, liters on bottom, so it's grams per liter.
Where did the Kelvin cancel out?
The temperature, right?
Right, because we have 336 Kelvin right here, and we're dividing by a Kelvin. So we're gonna, that's
Oh.
okay. Kelvin divided by Kelvin is nothing.
Will grams per liter always be the measurement
The
for
density.
density?
Yep. That's what you'll get your units as, and then it might ask for like grams per milliliter as your units, so you'll have to change it then to milliliters.
Well, what if, like, the stuff that they give us at the known part, what if it's in milliliters, wouldn't that change it back to liters?
We're gonna change that to liters, right? So whenever, because we're using R, whenever we use R, we have to use liters.
I thought R was liters per atom per mole per Kelvin.
Liters times ATM divided by
Yeah.
moles times. Okay. Oh, we have one more. Let's go with, well, let's do this first one together. The density of gas was found to be 2.0 grams per liter at 1.5 ATM and 27 degrees Celsius. What's the molar mass of the gas? So this time they give us the density, so we have 2.0 equals, pressure is 1.5, right? We know molar mass? No, that's what we're looking for, so we're gonna put that in big M. And what goes on the bottom? RT, so we have 0.082 times our temperature is 300. Good. So we're gonna have to solve for M. So you're gonna take 2 times 0.0821 times 300, right, first? And then you'll divide by 1.5.
Grams.
Grams per mole. Everyone get that?
I haven't tried yet.
pressure of 550 torr and a temperature of 25 degrees Celsius.
What's torr stand for?
What's torr stand for? Remember?
That's a big standard.
It's one of those standard units that we can use, and torr was equal to what?
760.
So 760 torr were equal to 1 ATM. So
Do
we're
we
gonna
divide it?
convert that into ATM, right?
So would you divide it by 760?
Yep. We're gonna have 551 torr,
1.38.
1 ATM equal to 760 torr. Oops. That's 760 torr.
Not 0.735.
Because remember, since we're using R, we have to be an ATM. That's why we have to switch that first.
Do we have to write it like that, or can we just put 551 over 760?
If you know you're gonna divide, but this just shows you that that's why you're gonna divide. It's gonna Okay, so density is equal to PM over RT, right? What's the pressure? Well, we don't use 550 millimeters.
0.725.
0.725. What's the molar mass?
40.
Yeah, we can round to 40 on this one.
It's okay if we round.
As long as it's really close. If it were 39.8, I would round. And then R is 0.0821. Their temp, 298. So this equation was pretty simple. It's getting to where you have the right units. And that one was a little different. So let me calculate that.
One.
1.1? 8.
1.19.
Would be our units?
Grams per
Per liter. I actually did Avogadro's law already. I've changed the slide around. Okay, stoichiometry of gases. The coefficients of a balanced equation indicate volume ratios. We kind of did this one on that little worksheet. When we're at the same temperature and pressure, and it's based on Avogadro's law, that so like if we have 3 H2 plus N2 gives us 2 NH3, right? This balanced equation is basically saying 3 H2 molecules plus 1 N2 molecule gives us 2 NH3 molecules. So we're going to be able to use this as volume ratio here, like 3 molecules plus 1 molecule equals 2 molecules of this, or 3 moles of this plus 1 mole of this equals 2 moles of this. That one we used a lot when we did stoichiometry, that middle one. But we can also, with gases, we can use 3 volumes of this plus 1 volume of this gives us 2 volumes of this. We're using the coefficients for that. So I'll just show you what we mean by this when we look at this. Propane is a gas that is sometimes used for cooking and heating. There's an equation for the combustion of propane. Does it look balanced? We need 3 carbons.
Yes.
8 and 8. And 10 and 10. Yep. So what's the volume in liters of oxygen required for the complete combustion of 0.35 liters of propane? Okay, if we're at the same pressure and temperature, we can take 0.35 liters of propane, C3H8, and we can use our coefficients as conversion factors in there. So our conversion, what is our coefficients right here. So we want 1 liter of C3H8. We go 5 liters of O2. Here. So just like we converted mole to mole, we're converting liters to liters. Or whatever volume. As long as the volumes are all equal, we have to use the same volumes. Doesn't matter which unit of volume you're using.
Where'd you get the 5 from?
The 5 came from the coefficient in front of oxygen.
I don't get it. Why are we finding oxygen or ask for carbon dioxide? We use the
No,
carbon
the first
dioxide.
question asks for oxygen.
Oh, got it.
First one asks for oxygen. Then we'll do carbon dioxide. So 0.35 times 5 is
1.75 liters oxygen.
1.75 liters of oxygen.
I'm not seeing where it asks for oxygen.
Is it not in your notes?
No, it's there.
Oh. And then the second part of that is asking for the volume of carbon dioxide, so we'll be doing it the same way. We have 0.35 liters of C3H8. And remember, in order to cancel our units, we have to have 1 mole C3H8, and what will be on top? Oh, not mole. I used to use mole. 1 liter. On top would be 3 liters of CO2. Right, from our coefficient here. The amount of amount of carbon dioxide that we're going to produce is
2.25.
I got 1.5.
No,
Right, we shouldn't get a bigger number than 1.75. So there's an example of the stoichiometry using the liters to liters or whatever. So now, next problem. Xenon gas reacts with fluorine gas to produce the compound xenon hexafluoride, XeF6. Write the balanced equation for this reaction. And if a researcher needs 3.14 liters of xenon hexafluoride for an experiment, what volumes of xenon and fluorine should be reacted? We're going to do the same temperature and pressure. So we need a balanced equation first. So we have xenon plus fluorine gas. Remember, fluorine is diatomic, so we have F2. They produce XeF6. So to balance this, we're going to need 3 here. So if we need 3.14 liters of XeF6, how much of all the other reactants do we need? So we have 3.14 liters xenon hexafluoride. And we have coefficients of 1. And let's go to xenon first. So we have 1 liter of Xe. So we would need 3.14 liters of Xe. We're using our coefficients here. It's a 1-to-1 ratio. And the other reactant, let me just erase this part here. And the other reactant is fluorine, and we have 3 for our coefficient, so 3 liters fluorine. So we would get an answer of 9.42 liters of fluorine. So that is how much reactants we would need. I'm going to rewrite out xenon. There we go. Okay, simple. We had to write an equation that time first, but still using our coefficients.
Next problem. Calcium carbonate, also known as limestone, can be heated to produce calcium oxide. The balanced equation is given here. How many grams of calcium carbonate must be decomposed to produce 5 liters of carbon dioxide gas at STP? So the first thing you might be tempted to try is just to change the liters of carbon dioxide gas into liters of calcium carbonate. We cannot do that because we are not they're not both gases. The only time you can use stoichiometry of gases is if both compounds are gases. So what we're going to have to do is find the number of grams or moles of carbon dioxide and then convert using our stoichiometry, using moles and grams, to calcium carbonate. So let's write our equations we could use. We could use PV equals nRT. That will give us the number of moles of carbon dioxide, which would be probably a good choice. Let's try that. We're at STP, remember, so the pressure at STP is 1. The volume we have is 5 liters. We're going to solve for N. 0.0821 is R. And at STP, the temperature is 273. Okay, so when we calculate this, let me calculate N real quick. We have 5 divided by 0.0821 divided by 273. I get 0.22 moles. And that's of carbon dioxide. So now we're going to have to convert carbon dioxide into calcium carbonate. So I'm going to do that on the bottom. So I have 0.22 moles of carbon dioxide. It's a 1-to-1 ratio, so 1 mole CO2 to 1 mole CaCO3. 1 mole CaCO3. Add up the masses, and you get 100.1 grams. Okay, our units, just check if our units canceled. Yes and yes. So we can just calculate this. And we get 22.3 grams of calcium carbonate. There we go. Okay, last problem. Tungsten, a metal used in light bulb filaments, is produced industrially by the reaction of tungsten oxide with hydrogen. How many liters of hydrogen gas at 35 degrees Celsius and 0.980 atm are needed to react completely with 875 grams of tungsten oxide? So what do we need to do first? Well, we're looking for liters of hydrogen, and we know a temperature, we know a pressure, and so we know temperature. Let's write this down. Temperature is 35 degrees Celsius. Remember, we have to be in Kelvin, so 35 plus 273 is 308. So let's write that down. 308 Kelvin. We know a pressure is 0.98 atm. We're looking for volume, right? So which equation could we use to find volume when we know pressure and temperature? I would say we should use PV equals nRT. The only thing we need to do is find N. And since tungsten oxide is not a gas, we can't use just the stoichiometry of gases. What we're going to have to do is change grams of tungsten oxide into moles of hydrogen gas. So I'm going to do that up here. So we have 875 grams of tungsten oxide is WO3. Now remember our stoichiometry. We have grams of tungsten oxide on the bottom and 1 mole on top. And let's see, the mass of tungsten is 183.85 plus 16 times 3, 231.85. There we go. And we have a 1-to-3 ratio, so we have 1 moles of tungsten oxide is equal to 3 mole of H2. There we go. We're in moles of hydrogen, which is what we kind of wanted. So when we calculate this out, we're going to have times 3, 11.32 moles of hydrogen. So now we can plug that in down here. So we know P is 0.98. We don't know V, that's what we're looking for. N is 11.32. R is always 0.0821. And temperature was 308. So our volume is going to equal 292.14. So 292.14 liters. There we go. So that time we didn't use stoichiometry gases, but we kind of integrated everything that we've learned so far. So very good. Dalton's law of partial pressures. Okay, the partial pressure of a gas mixed is the sum of all the individual pressures of that gas. They're called partial pressures when you have the separate individual pressures of the gas. So the total pressure of the gas is equal to the partial pressure of A plus the partial pressure of B. Here. If we do some math here, we have, because R and T and V, they're all the same because we're at the same temperature, same volume, since the gases are mixed together. The only difference is the number of moles, so we can separate that out. And if we rearrange all of that here, we get to where we have a mole fraction. The mole fraction is equal to Ni initial divided by N total. Here, so that's considered our mole fraction. We will be using that. And if we want to know partial pressure of one, we can just use our mole fraction times the total pressure then. So if we have partial pressure here, gas 1 plus gas 2, we're combining them, getting a new pressure. So if a mixture of gases contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon, calculate the partial pressures of the gases if the total pressure is 2 atm at a certain pressure. So let's start with neon. So if we want to find the partial pressure of neon, we're going to have to use our equation. P of neon, the partial pressure of neon, is equal to the mole fraction of neon times the total pressure. We know the total pressure is 2 atm. So we need to find the mole ratio of neon. The mole ratio of neon is going to be 4.46 over, we'll have to add up all the moles of all the gases. So 4.46 plus 0.74 plus 2.15 is 7.35. So that answer, that mole fraction, is going to be 0.607. So we can plug that in here. So the partial pressure of neon is going to equal 0.607 times the total pressure is 2.0. And we will get times 2, a 1.21 atm. Yes. Okay, we'll do the same thing, but we'll have to have a new mole ratio for argon. So it'd be 0.74 divided by 7.35, a 0.1 total or partial or mole ratio, excuse me, and multiply that by the total pressure of 2, so you get a 0.20 partial pressure of argon. And again, for neon or xenon, 2.15 divided by 7.35 times times by 2, so we'd have a 0.585 ATM. Now one way you can check yourself would be add up all those partial pressures, and we should get about 2.0 because they're all supposed to equal 2, and I get 1.995, so basically 2. So we're there. We got the right answer. Let's try another one here. Sample of natural gas contains 8.24 moles of methane and 0.41 moles of ethane and 0.116 moles of propane. If the total pressure of the gases is 1.37 atm, what's the partial pressure of these gases? We're going to do it the same way. So we're first going to have to find their mole fractions. So let's find the total. We would have 8.24 plus 0.41 plus 0.116, 8.766. So if we want to find the partial pressure for methane, CH4, we would have 8.24 divided by the 8.766, and that would give us a mole fraction of 0.94. Multiply that by the total pressure is 1.37. 1.29 ATM. And if I go through and do this for all the other ones, and propane, 0.41 divided by 8.766 times 1.37, 0.064 ATM. And last one, 8.766. No, do that. 6 divided by. I get a 0.018 ATM. So that's all of my partial pressures. Again, when you add them up, it should be equal 1.37. So you can check yourself there. Okay, this one's going to be a little bit different. Halothalene has the formula of C2HBrClF3. If it's a non-flammable, non-explosive, and non-irritating gas that's used as an inhalation anesthetic, supposing we have 15 grams of halothalene vapor with 23.5 grams of oxygen gas. If the total pressure of the mixture is 855 millimeters mercury, what's the partial pressure of each gas? So we'll find the mole fraction, but before we can find the mole fraction, we're going to have to change grams into moles. So let's do that. 15 grams of the, I'm going to call it HT, halothalene, so we don't have to write out the whole thing. So let's find the molar mass of HT. Let's see, carbon is 12 times 2 plus 1 plus bromine is 79.9 plus chlorine is 35.45 and fluorine is 19 times 3. So I have 197.35. So our number of moles here is 0.076. Now let's do oxygen gas. So 23.5 grams of, remember oxygen gas is diatomic, O2. So we have 32 grams of O2, 1 mole O2. So 23.5 divided by 32 is 0.734. So the total number of moles
then is, well, that's 0.076, 0.81. So the total is 0.81. So if I want to find the partial pressure of halothalene, our mole ratio would be 0.076 divided by 0.81. So I get 0.09 multiplied by the total pressure. Now since we're not using R, we can leave it in millimeters mercury, but our units will be millimeters mercury. So 80.22 millimeters mercury. And then the partial pressure of O2, I have 0.734 divided by 0.81 for my mole ratio is 0.906. Multiply that by the total, and I have 774.77 millimeters mercury. So same idea, we just had to do one extra step at the beginning. Now a lot of times gases will be collected after they've been bubbled through water, and when you do that you're going to have some water vapor collected within that sample, and the gas bubbles displace water in an inverted jar, and the pressure is equal to the sum of the pressures exerted by the gas and the water vapor. So here's an example. If we're using O2, it's just like Dalton's partial pressure law, but we're just going to always have partial pressure of water, and that will change depending on the temperature that it's at. Here's an apparatus. If you have this, they're bubbling off gas. The gas will move through here, and then it will bubble up through this jar, and it begins to fill up with gas. Okay. If we look at, you're going to have to use your books a little bit for a chart. Let me find it in my book quick. Page 152. There's a table in the bottom left-hand corner that gives you the pressure of water vapor at different temperatures. It will depend on what temperature the volume is at, or the gas is at. So in this case, oxygen gas is generated by the decomposition of potassium chlorate, and it's collected. The volume of oxygen collected at 24 degrees Celsius and atmospheric pressure of 262 millimeters mercury is 128 milliliters. We're going to calculate the mass in grams of oxygen gas obtained. So again, we have the total pressure is going to equal partial pressure of oxygen plus the partial pressure of water. If you look at the last sentence, it tells you that the water vapor pressure at 24 degrees Celsius is 22.4 millimeters mercury. So we're going to fill that in. And the total atmospheric pressure is 762 millimeters mercury. We're looking for the partial pressure of oxygen, and this is 22.4. So the partial pressure of oxygen, you just subtract the two, and you would get 739.6. There we go. So now we have the partial pressure. Now we're going to go backwards of what we did. We're going to actually, let's see if I have room. We're going to use that as a pressure in our molar mass equation. So we have mRT over PV. I'm going to erase this part right here so I have more room. And what do we know? We know the molar mass of oxygen is 32, so we have that part. We're going to calculate the mass, so we need M. Do we know R? Yes, we know R. And the temperature,
RT is 24 degrees Celsius, which is 297 Kelvin. Okay, the pressure that we're going to use, we're going to have to change this into ATM, so we're going to divide by 760. So 739 divided by 6, or 0.6 divided by 760. It's because 1 ATM is equal to 760 millimeters mercury. I have 0.973 ATM. And our volume, 128 milliliters, we have to be in liters, so 0.128. So we're going to solve for M. So once you calculate for M, you get 32 times 0.973 times 0.128 divided by 0.0821 divided by 297. And I have our final mass, I'm writing at the bottom, is 0.163 grams. Okay, so we kind of used a little extra information, used our other equations that we learned just a little bit ago, and we found the mass then. Very good. Okay, the hydrogen gas generated when calcium metal reacts with water is collected and the volume of gas is 30 degrees Celsius. And the pressure is 988 millimeters mercury and it's 641 milliliters. What's the mass in grams of the hydrogen vapor obtained? So, same thing as the last one. We are going to find first the partial pressure. The partial pressure, maybe. Let's see if this works. It goes right. Okay, so we're going to find the partial pressure of hydrogen, though, this time instead of oxygen. Okay, our partial pressure of, our total pressure is 988. Partial pressure of hydrogen will be 31.82. So partial pressure of hydrogen is 956.18 millimeters mercury. So now we're going to use our equation again. What's our molar mass of hydrogen? Is 2 equals, we're looking for M. R is 0.0821. Temp is going to be 303 when you add the 273. Divided by the pressure. Okay, again, we're going to have to divide by 760 to get ATM. And that gives us 1.26. So 1.26. And our volume, change to liters again, 641.641. So when I calculate for M, times 2 times 0.641 divided by 0.0821 divided by 303, and the mass I get is 0.065 grams. There we go. So that's kind of mixing and using everything that we've learned so far. Very good. So that's where we're going to end for right now.